So, good afternoon. My name is Luca Miccio, and I'm an undergraduate student of the University of Modena and Reggio Emilia. And today I will tell you something about the I/O scheduler. I know it's a bit off topic, but this presentation is divided into two parts. I will cover the first part, which is about the I/O scheduling and the current status of the I/O schedulers in the Linux kernel. Then there is a second part, and my professor Paolo Valente is going to tell you something about the power management. And we are here because we are trying to build a bridge between the I/O schedulers and the power management. So uh, these are the main topics. First of all, I will tell you something about the last general developments in Block.io. Then I will show you also the problems related to the block layer. And then I will present to you a possible solution for these problems. And finally, I will cover also the integration between Android and this solution, which is the PFQIO scheduler. And then there is the part of my professor. So let's start. So what is the block layer? Well, a generic block layer is an abstraction for the block devices. And these block devices may be physical or logical. And the block layer receives the I/O requests, and it's responsible to pass these requests to the block devices. And then the I/O requests are scheduled for submission to the device by the I/O scheduler. So what is an I/O scheduler? Well, it's a block layer component deciding the order in which the I/O requests are to be served. And especially if we are in a scenario where there are more processes that are competing for the same storage device. So how does an I/O scheduler make its decision? Well, there are four main goals to achieve: high I/O throughput, low latency, high responsiveness, and fairness. And these goals are very difficult to achieve because, or even impossible, because they contrast with each other. For example, it's very difficult to achieve a high I/O throughput with a low latency. So now what is the current status in the Linux kernel for the block layer? We have two main frameworks for I/O stacks. This one is the so-called legacy block layer. Here we have three I/O schedulers available, which are CFQ, Deadline, and NOP. And these schedulers decide the order in which the I/O requests are inserted into this request queue. And note that there is only one request queue, and this is a problem for all those storage devices that are very fast and highly parallel. To solve these problems, there is another I/O stack, which is the block-MQ stack. It was developed mainly by Jens Axbo, which is the main maintainer of the block layer in the Linux kernel. And it was added in Linux from the version 3.13. And yes, it solves the problem of the single request queue by turning this single request queue into multiple and independent queues. And yes, there is more about block-MQ, but this is just an idea of what a block-MQ is. And yes, there is no I/O scheduler available yet for block-MQ, but as I am about to show you, not for so long. Okay, now I have set up the context of block layer, I/O schedulers, and all that stuff. Let me show you the problems. Okay, so what is happening now with storage devices? They are fast, we know they are really fast, and they will become faster and faster. So what are the main consequences of that? Well, sure, no more latencies, so no lag, no frame drops in video playback or streaming, no gaps in audio playback. So you may think everybody is happy, right? Well, not everyone. For example, here we have a list of posts. For example, there is one that is very interesting. This last one. Occasional lag, disable auto-update in Google Play Store settings. Well, the main problem is the lag, even with modern devices. And instead of going on with words, let me show you these problems with a recorded demo that we made. Here we start a common application, Facebook in this case, on an Android system on the IK board. Okay. Okay, so this is divided into three parts: live video playback, and throughput. These are the software version that we are using. Thank you. Thanks. And okay, also the hardware of the IQ. Okay.
The music was chosen by Luca. I think it was very nice.
Okay, here contacts and more. Okay, first test. We are about to see the startup of the Facebook application with no. And the result is the same with any scheduler because here we are using no I/O in the background. Okay, it takes about 6 seconds to start up. Now let's add some workload in the background. Yes, this is just a part of workload generated by one or more file copies, but the tests with also file copies in the background are about to come. And the results are the same with CFQ or deadline. Okay, just for reference, we have the idle case on the left, and on the right, we have not with the workload in the background. Too much to wait. Okay, it takes about 20 seconds to start up the application. So before we continue this demo, let's jump back to the presentation. Okay, now we saw the problems. Well, these problems are not related only to the Android system. They affect PC Linux distributions too, with both HDDs or SSDs. I have no time to show you our tests that we made on HDDs or SSDs, but here there is a pointer where you can find a demo showing that these problems affect also those fast devices as well. So we saw the problems, and now I will show you a possible solution for these problems, which is the BFQ I/O scheduler. So yes, BFQ is an I/O scheduler, and why another I/O scheduler? Well, as we have partially seen, block schedulers are not performing very well. They are not very successful. In contrast, BFQ really guarantees high responsiveness, low latency to soft real-time application. For example, we have no more frame drops, and also high throughput. Well, let's see BFQ at work. So let's see what BFQ can do, and let's go on with the demo. Okay, we were here. Okay, now it's the turn of BFQ. We are using the same workload as the previous test. Yes, yeah, get paid to be surprised. Okay. Okay, BFQ takes about 7 seconds, 1 second higher than the idle case. While with NOP, we have a startup time that is more than 3 times as high as we know background workload. Okay. Now, what happens if we add writes? Well, let's see it for 2 real use cases. we will give one file transfer to NOP for NOP and two file copies for BFQ, and this one is a much heavier workload. So we have, just for reference, as always, the idle case on the left. Okay, BFQ. Okay, it takes 11 seconds with BFQ, while with NOP we have problems, because only when the background workload terminates, the application starts. We have problems with BFQ too because of the virtual memory stack issues that are out of BFQ control, but they are solvable using BFQ, and we are working on that too. And yes, there is a bit too much to wait for NOP. The application is still loading. Okay, now second part of this video. Okay, we are about to see a playback of a video. We are using the same workloads as the previous test. Now we are starting the video player. Okay. And the BFQ takes about 14 seconds to start up. While obviously with NOP, as with Facebook, the player will start after a long time. And here we simply jump to when the application starts. In while as you can see, there are no problems with the video playback of BFQ. There are no problems, no frame drops or anything. And with NOP, after all the time spent waiting for the application to start, we have also problems with the application also freezes. Yes, as you can see right now. And now. Yes. Okay. Third part, the final one, the last one, we have measured the throughput, and we consider BFQ and NOP because NOP proved to be the best I/O scheduler in terms of throughput, and we are using these workloads. So 3 readers sequential, 3 reader random, 2 reader and 1 writer sequential, 2 readers, 1 writer random. And the idea is to measure the throughput with parallel reads and writes. And we are using only 1 writer because more writers penalize more. Okay, and these are our results. Okay, for the 3 sequential readers, we have virtually the same throughput with both schedulers. While with the 2 readers and 1 writer sequential test, we have the throughput that drops with NOP because NOP privileges writes, which are slower than reads, much slower than reads. Then before we finish this demo, let me show you also how BFQ, what BFQ is, and let's find out also how does BFQ work. So BFQ can be divided into 2 main components. The first one is the accurate proportional share weight-based scheduling engine, which guarantees to each process its share of this throughput. Then there is a set of heuristics, of low latency heuristics, which assigns a high weight to applications to privilege. So how can BFQ guarantee such a low latency? Well, by simply using the throughput for the right I/O requests. And yes, if needed for latency, BFQ sacrifices the throughput, but not that much. And the actual added value is guaranteed both low latency and a high throughput at the same time. Well, what happens if we have no application to privilege? Well, BFQ simply aims only at maximizing the throughput. Okay, and this is just the BFQ page. Here you can find more details on how it works, pointers to demo, also pointers on existing papers on BFQ. everything about the BFQ project is here. So if you want to know more about BFQ, check it out the website. Okay. Now, what is the current status of this project? Well, BFQ is landing into Block MQ with the name BFQ MQ. And there is a collaboration with block maintainers and developers, which is in progress, and the framework of Jens Axpo is complete. This framework allows BFQ to be added to Block MQ. And yes, the second BFQ patch series were submitted on the 1st of March. So we are aiming for the version 4.12. Okay. As I have showed you mostly a demo with on an Android system. So what about Android? Well, last year I started working on this project, and I'm currently working on this project, which is about the integration between the BFQ IO scheduler and the Android system. So the results are very exciting. That does seem a serious problem also for Android. And we are trying to push support with Google, the Android kernel team, and also with Linaro. And there is a Linux kernel SUS 3 with BFQ already integrated, and it's available at this link on GitHub. This kernel is used on the IKEA, and we support the 4.4 and 4.9 version. Okay, now just a look into the future for both next storage devices, and BFQ. So next ISP devices, yes, they will become faster, and they will have more and deeper internal queues, and they will suffer from the same latency problems. And to achieve a high throughput with those internal queues, they must be kept filled with high enough number of IO requests. And what about BFQ? Well, BFQ has its limitations. It's not designed for extreme parallelism and also for deep queue devices. And it has a higher overhead than a minimal scheduler. So let me show you with the last part of the demo this problem. Okay. Now, the last tests, the random ones. So here, as you can see, the throughput drops with BFQ, mainly because the random I/O involves many more IOPS, and also, as I have told you, BFQ has a higher overhead per I/O, and also the CPU is made by many slow cores. So the main consequence of that is that one core gets saturated, and yes, we are working on that too, on this problem of the overhead. Okay, this is the end of this demo. And let's jump back to the presentation. Now, what about the future with the Android integration? Well, as I have showed you, we have problems with the virtual memory steps, so further important steps are needed, and we will submit BFQ to the Linaro kernel 3 with the guide system. And yes, furthermore, I will make the test suite that we are using for this demo available and easy to use to everyone, so that everyone can test the devices. So that's the end of my part, and now I will give the floor to my professor. Thank you.
I'm the professor in question. My part will be rather quick, because this is the state of the art of I/O scheduling and power management. It is nothing. So, so basically, I'm here to try to understand where we could start from. and we can start, I don't know, I can try to start by proposing an idea. The most natural thing that I have thought is to try to reproduce the same scheme that is now being used for the CPU case. So collecting information from the scheduler, for example, utilization, like in scheduler, and try to use this information to control the parameters that somehow affect the power consumption. I'll try to think about the components that may be involved in this. So probably it has to do with everything along the path. So from the interconnect to the I/O buses to, of course, the storage devices. And how to intervene, I thought about the two strategies that came to my mind are first idling, and the other one is controlling somehow OPPs or something like that. So as for idling, well, I think that one case in which one uses idling is when you don't have any I/O at all. So in that case, I think it's nothing so surprising. And I guess that many devices already have some auto idling mechanism. I don't know whether can I say being more aggressive on this can be beneficial. This is something I'm trying to ask too.
So Linux used to have a laptop now, but I have no idea if it still exists, where we would inflate the write-back cache until it burst in order to delay spinning up the rust that was in those laptops. And once also when a read request came in that could not be satisfied from cache, once it was spinning, we would flush the entire write-back cache.
Yeah.
I don't know if any of that still lives.
Okay.
Yeah, that is basically avoiding doing I/O using the cache.
Yeah. Okay. Anyway, the other thing I thought about is.
It doesn't work.
I don't know.
The other thing I thought about is maybe doing idling also during I/O. I don't know, because I don't know whether there are some, I mean, meaningful kinds of I/O for which you can idle something before the next I/O request arrives. I don't know. I think maybe the I/Os arrive too quickly to do something like that, but this is something else I thought about. Maybe since the granularity of I/O is coarser than that of a job on a CPU, maybe there are cases where you have to wait so long that maybe you can add something, I don't know. And of course, the other option is somehow setting the operating point of the components involved. And I don't know if idling is impossible. Probably this is the only way to go. So somehow you set the parameters of the components involved. So other questions. What are these components? Another important question for me is what are the components for which it is possible and useful to set OPPs? I guess interconnect.
Yes. We have a framework, but we are working on the framework for that.
Yeah, and we already talked about this with Vincent.
NVMe?
No, it's a bus scaling framework where the goal is to scale the interconnect bus depending on the bandwidth request of each device. Saying I need
And that's PCI, right?
No, not PCI. Interconnect. Not what in ARM it's called NOC bus. So it's really inside the SOC. The PCI can be connected to that. That's really SOC specific.
So it's strength based.
Yeah.
Which is different to have left.
No, it's not network. It's about the device, and here it's really about the interconnect in the middle.
Yeah.
Instead of trying to monitor and to evaluate the load, we would like each device to say, I'm a SD card class 10. I need this amount of megabyte between me and the memory, and that's all. You don't even have to try to predict. You have the value.
Generally speaking, though, all of the work in the block layer so far has been driven by performance.
Yeah. Yeah.
So how does BFQ multi-queue work?
With respect to power management, you mean?
No, at all. I mean, I know BFQ because that's the EUVDF variant. But
Yeah.
how do you do multi-queue part?
Well, it's exactly the same. Just modify the interfaces to let it work inside block and queue.
So you have parallel copies, or do they talk to one another?
That's what I want to do. No, as of now, it's just one single instance. It's not, I mean, it's for block and queue, but it's not multi-queue.
Oh, okay.
Yeah. It's for block and queue dash single queue. Yeah, that's okay. It's this way, but yeah, this is something we will work on.
Yeah, it's multi-queue part.
Yeah, the real multi-queue. Yeah, yeah. It happened this way because it was the only way to have it in Linux, basically. But recorded, so I won't say anything else. Okay, and yeah, the other part, I don't know, the I/O bus. I don't know whether is it possible to. I really don't know.
So I know NVMEs have OPPs and I/O states,
Okay.
but I have no idea what timescales they operate on.
Also, they are PCI devices.
They're PCI devices.
So then there is PCI power management on those devices. You can use that probably. You can use the PCI power management if you know that they are idle. I mean that there are no.
But it's only about idle or not idle.
Yeah. So the PCI power management, I mean the standard one, it's mostly about idle and not idle. There is something called OSPM, which is actually state power management, but that's done automatically by hardware.
Okay, set the text.
And it's supposed to be taken care of itself.
Okay.
So yeah, those are the mechanisms that I'm aware of. As far as PCI devices go,
Yeah, breaks for every other system.
for the other things like flash, that depends on the interface, like between the flash device and the bus on the system. So they are hanging out of flash devices usually I2C or something else.
No, the SPI. Yeah, SPI, or parallel bus, we can mix and mix
So
those
those
data.
can be like driven directly sort of by by setting OPPs, but I don't know to what extent that is done.
So it's in terms of speed in that
Yeah.
case, I
And
guess.
for EMSCSD,
So for MMC, there is two layers.
Okay.
First of all, we have the actual storage device itself, which you can send specific speed commands to and put the device.
So that's again to switch off. I mean, it's not. Yeah.
Yeah, to put in sleep state or to switch off, it's different levels.
Okay.
Then of course you have the, as in any other case, you have a controller that's actually talking to the phone. And depending on the SSC, you can put the controller in the power station. That goes with all the SSC actually.
But you told me also about setting the speed of the device.
We can set speed, but this is more an SSC thing, I would say. Some controllers needs to be run in certain, they need to have a clock with a controller in a certain frequency and certain level of speed to be able to support different speed modes of the EMC or the SD card. So that's something that we haven't been we haven't been doing that for the framework MMC yet, because it's more or less, if there's a C and the MMT controller supports a high speed mode, we always select the frequency that we need to support high.
Right.
So it's not degrading.
Right now you're just trying to make a raised idle for the when you're writing to the.
From a high management point of view, yes.
Yeah. Do we have any core numbers about how much we can save if we reduce the frequency or reduce the number of signals compared to running to racing driver or in MMC or SD card?
So, I mean, there is data sheets for UNC.
Yeah.
UNCs you can look into to see how much.
Just to have an idea of how much we can.
But didn't you tell me you have also some numbers that you took, some measurements?
Yes, numbers about how much the car is
Consuming.
Yes,
Yeah.
I have some numbers.
I will ask you again. Yeah.
So that, yeah, EMLC is more for embedded, so obviously it does behave better.
Yeah.
But there is SD cards that is using an embedded world as well.
Yeah.
And those might be really, really, really bad.
Yeah.
It could be consuming like, I've seen the really worst case scenario is that you plug in an SD card, which is like some SD card from some vendor that doesn't care about power management, using 18, 15 milliamps constant.
Just plug it.
Plugging it in.
Awesome.
That's not really good. So if you plug that in a embedded product.
So somehow, if they are controllable, it makes
So experience shows that you have to be very careful about controlling power on devices like that, because sometimes they say you put them into a low power state and then they don't wake up later. Or similar.
But it saves a lot of energy.
Yeah, it does. But then, and because we had so there was a story involving SATA drives that have the feature that you could turn on and they should power manage themselves. So it turned out that it didn't work in a few cases at least.
Okay.
So
good to know.
Avoid that. And there are problems like that because those
Yeah, the same is true for ASPM.
Yeah, so they are tested in some cases. Let's just say, if they are tested, they will work. They aren't. It's like, yeah, the feature is there because this is PCI, for example, but.
Okay, so be careful.
So be careful, yeah.
Okay, so these are my questions, and I think that's all. If you have questions too, and that's all. Before I forget, I want to take the opportunity of being here just to say goodbye to everybody, because I think we will follow, attend only the next presentation. Then we have to go away. So I also say goodbye and thank you.